technological disruptions in the energy transition. This is Cleveland Jones, our professor, Cleveland Jones. This is Paul Taylor, consulting. And this is me, Armando Cavain. Let me remove this to talk something to contextualize a little bit. So there are many technology gaps in the energy transition, maybe in the energy addition, if you want, that need to be removed to have a more consistent transformation. And what are the desired solutions? This is the debate today. So, Paul Taylor, please, could you start with your ideas?
Sure. I mean, the dual challenge of meeting the growing energy demand while working to reduce carbon emissions is to create a constant stream. It's creating a constant stream of ideas with the potential to transform how the world produces and consumes the energy. So necessity is the mother of invention. Um, Renewable energy innovation, the worldwide demand for energy is increasing, and the innovation continues to focus on renewable energy production, the distribution of that energy, and the storage of that energy. And we're seeing more of a reliance on carbon-based fuels. But um, I'd like to open that up to discussion. Because we're seeing a lot of innovation in the renewables. We're not really seeing innovation in the petrochemical industry. Um, we Because we're trying very hard to get into the renewable energy sector. But the renewables, they have a lot of work to do. For example, these high voltage power devices, these are essentially transistor switches, and they are the building blocks for rectifiers, inverters, and converters, and which are used to condition power generated from renewable sources, and deliver those loads to the grids and the storage systems. Now, the power density is less critical in renewable power applications, but the solution size still matters, particularly for residential systems such as home solar. That, and the, so everything you have must fit neatly within the confines of a home residence. There's no point having 30 cubic meter um, switches or inverters that are bigger than your house. Um, so most of these innovations are for the mobile sectors as well as the residential renewable sectors. But we have things like silicon carbide, which continues to be popular for inverters and other power conversion circuits for their high power densities and high voltage capabilities. And then lastly, we have storage. How can we store the energy? Because we know that wind farms and solar are very intermittent sources of power. So how do we store the power that they're generating, or the excess power that they've generated, into an efficient system that can be tapped on when those wind farms are not working because it's not a windy day, or it's a cloudy day and the solar farms are not generating any power. We've seen advances in the energy and the storage capabilities, but those advances are measured in years, not months. They're very, very slow advances. We've seen lithium ion batteries for quite a long time, but those batteries are expensive and they're not very large. They don't really have grid scale applications. They make it very difficult to meet long term or long duration storage requirements, and therefore they're not economically viable. So these lithium ion based storage solutions they address the shortcomings, and those shortcomings will continue to be a major area of focus for the future development.
But Paul, do you expect to have a totally different way to store energy, or something like I could see something continuous growth and qualification?
That's an interesting question. When I was a kid, I remember reading this series of science fiction books. I can't remember who the author was, where the solar system was being invaded and Earth and humans were fighting for their existence. And everything came down to batteries. And that was back in the 70s. Batteries were seen as the savior. And now we're seeing the same concept that batteries have to be, or new types of batteries are the only way forward, because we know how to generate the power, but we don't know how to store that electricity.
Paul, there's a interesting thing that you mentioned, because batteries have been seen as, key to make everything possible, because electrification presupposes, of course, having electricity available all the time. So this would be the most immediate way of imagining energy availability in terms of electricity. But you see, there's a big disconnect here, because even a few years ago, when solar was becoming more prevalent and so on, and the Tesla batteries were making big inroads, people were saying, okay, now every house is going to have a big battery pack, not a little battery pack, a big battery pack, the size of a
Bigger
car,
than a
and
house.
they can run cars and power the house for weeks. And of course, that didn't pan out. Tesla did install big sets of batteries in Australia and many other places, but this didn't work out as fast and as far as we imagined, even though those things were, very close to being developed.
So, Cleveland, only to add on your question, very, very important questions. So the expectation is that you have a totally different way to store energy instead of only better batteries every day. Paul.
Well, I'm not an electrical engineer, but I really hope that we do see better ways of storing the power on a national scale rather than residential scale. Scale is the important thing here. We've got to remember that you don't need very many batteries for a house. You still need a lot of batteries. But we get into a completely different kind of discussion, because we've got to think about the mining and the minerals and the elements that go into the making of those batteries. But we really have to find a way of scaling up from batteries in the residence to batteries that can power factories, not refineries, but a much larger scale operation.
Yeah, but that's a good point, because Cleveland knows very well. He's a physics specialist. So the limitation is from the minerals and metals. So there is a thermodynamic limitation, or you can, let's say, have a disruption in these technologies.
Paul, let me say this. I think what Kavai is saying, the limitations. I'll let Paul answer this later, but there's several levels of limitations. The physical limitations from the physics side in batteries is very important, because storage is one thing, but when you talk about batteries as a piece of equipment that stores electricity, then you have physical limitations as to energy density and so on. You can't expect to have a battery with as much density as a tank full of petrol. It's just not feasible in that way. But and this goes back to physical realities of chemical reactions and stabilities and all that kind of thing. But of course, we can have a lot of advanced technologies that improve technology currently, even in storage of battery storage, energy density, and so on. We are so far from some of these limits, even though they exist, that we can improve them a lot. That's the other side, the good and the bad. I mean, the bad side is that there's limitations. The good side is that we have far to go before we reach all of those limitations.
Perfect. Let me share on that. We have compliments from Jorge Oliveira, is a friend of us, of other podcasts. So he is saying in Portuguese, boa noite.
Good night also, Jorge.
Yeah, perfect. Thank you, George. Please go ahead, Paul and Paul.
Well, I think we should move to the next slide.
Sure.
Because one of the interesting things that we're getting with innovations is a digital transformation. And I found some interesting material on the BP website. There's a chap there called Dan Walker, and he leads up the evaluation technical team. And he said that they're constantly evaluating, assessing, and analyzing hundreds of new technologies that have a potential to impact the company positively or negatively. And they're constantly scanning to identify and track those technologies. One example he gave was back in 2015 with the emergence of battery and fuel cell technologies. But just a couple of years later, in 2017, they were looking at blockchain and the next generation, the association with blockchain and the next generation of wind technology. And that is their focus. Now, we may have heard of blockchain as a word, but do we know what it is? Blockchain is essentially, it's a digital ledger that creates and stores records called blocks, which are linked together in a chain. So the data in a blockchain is time-stamped, the information is recorded, it cannot be altered retrospectively, and this makes records verifiable and permanent. And those records are stored in a transparent shared database. The blockchain technology enables the direct exchange of assets or tools in a secure way, without the involvement of intermediaries that can manage the exchange. But how does that work in the energy industry? Blockchain in the energy industry offers an opportunity to create a disruptive business model in trading, supply chain management, and retail. But it can also be used to reduce operational risk and transactional cost.
But Paul, please, but this does not create energy, does not disrupt anything, only optimize or only increase efficiency of the process, no?
That's true. That's true. But the energy sector, you still have to sell that energy. Okay.
Paul, I think some of this goes to the fact that if we say that something that improves marginally a process, that's not so disruptive. But remember, there are tremendous losses all throughout the energy chain, from production to eventual use, so that a process, blockchain somewhere on the chain or in many places, that can improve efficiency or reduce losses or risk or facilitate the process can actually be considered disruptive, because there's no real other ways of improving the whole process and the whole chain by 5-10%, and in some cases more, and especially reducing risk, which is sometimes, the major limitation. You can't do certain things because you're going to be exposed to risk. So if you can now bring a new technology from outside, for example, the energy industry, certainly outside the oil and gas industry a while back, and all of a sudden you bring it in to the industry that allows efficiency and functioning at a new level, I think in many cases that is even more attractive to industry because they recognize that as something that is relatively low risk to implement, and the results are very reliably positive, even though they're not doubling sometimes.
That's right, because when you're working with power plants, blockchain can be used as a powerful tool.
Yeah.
It allows you to trade any excess power generated from, for example, the solar voltaic cells or fuel cells without any need to use a centralized grid. And you can improve the efficiency of the system that way.
One of the ways that we can visualize this easily is that everybody is now very concerned, as they should be, about the integrity of a lot of these systems, from gas pipelines to transportation control systems to operating refineries and energy systems, because of malware, concerted attacks by individuals or countries or bad guys, and the risks are so tremendously large. Imagine if a major refinery were to be put offline, you could even enter into risks of plant integrity. So something that can allow you to operate near the optimum or near the maximum operating range, that can be transformative. All of a sudden you're much safer because you have this tool that is operating within the system to make it work safely at a higher level. That is nowadays perceived as very important.
You mentioned more reliant and the system, maybe.
Sure.
Like that.
Once you have a safety process in place, so that you are confident that it's not so subject to interference, then you can operate it at a higher level, maybe closer to the maximum operating. I'm thinking of refineries, for example, but the same thing applies to solar farms that are sending out electricity, and oftentimes because of interference in the grid and so on, they have to curtail their energy shipment unnecessarily, it turns out. But if you had a system that can figure all of this out, artificial intelligence and machine learning, optimizing the whole system, and then everything being reliably controlled, then you can say, well, we can use more of this energy and we can ship it out instead of just wasting it or curtailing.
Yeah, but I'm insisting that the problem in this focus is that we are only improving efficiency.
Exactly.
We are not disrupting anything.
This focus still,
Yeah, but we need to be more efficient with renewable energy because of the intermittent nature of it. So, what else?
3D printing, where does that fit in, Paul?
This is an interesting one, because the concept of 3D printing has been around for more than 30 years. But with the increasing sophistication of the technology, advances in the digital technologies and the lower equipment costs, it's now on the verge of becoming mainstream. Now, Accenture, they said there are two drivers for the oil and gas industry with 3D printing. The first is to reduce costs and increase operational efficiency by producing new parts that weren't available to manufacture, or improving the design of current parts to enhance safety, efficiency, and reduce the costs. Now, I remember once a drilling engineer was saying that he was being charged $150 for a nut of a certain size. And he was able to go and find somebody very locally, like a car mechanic, who would make him one for $8.
Yeah.
Well, you can print them these days.
Yeah.
Now,
Very
the other
efficient.
thing is, what the Action Tour said was that downstream 3D printing represents a potential new revenue stream for the oil and gas companies, because they can provide the chemical powders and plastics used by the ink of these printers.
Yes, and even though we're used to thinking of the oil and gas industry, where major savings have come about from sourcing parts and so on, with locally produced parts and so on, this applies also to other industries and even to industry in general, so that we can see that industry can become more energy efficient if they can operate their equipment, maintenance including, at rates and at levels that were impossible before. So this is technology making possible efficiencies, including in energy use, not just in generation.
Yeah.
And for e-fuels, Paul, your last point, please.
E-fuels. Now, e-fuels are essentially, it's an umbrella term for liquids or gaseous fuels that are produced using electricity as a prime source of energy. The common constituents being carbon dioxide, nitrogen, and water to form compounds that can serve as a fuel. And they have the potential to disrupt the existing fuel space in the long term if power is at a sufficiently low cost. Now, these fuels, they can be compatible with the current industrial infrastructure and supply chain and can be stored efficiently at low cost. But the energy needed to convert the CO2 to liquid fuels or chemicals is quite considerable at the moment, and will need to come from renewable sources such as wind or solar. The development of efficient, low-cost catalysts is important and has been accelerated with advances in material science and artificial intelligence. But everything is still in its early stage of development, and questions remain about the economic feasibility of e-fuels and its commercialization. At present, e-fuels cannot compete with biofuels or traditional fossil fuels, but they are similar to biofuels, and they would benefit from carbon pricing. The production is in its infancy, and there's a lot to overcome, including the capital cost per unit of output power consumption. But it's
Great.
with the cost of batteries coming down and the move to transport electrification, there may be less incentives to develop e-fuels as an excess renewable power for storage medium or liquid fuel. So it's
But Paul,
could be there in the future, or they might just die a death.
but the other side of the coin is that e-fuels are fuels, and fuels have a place, at least for the foreseeable future, as an energy carrier that is applicable in airplanes and automobiles and so on.
Trains.
Trains. So that the e-fuels have at least a generation of potential, because they fit into existing fuel systems. I mean, you can substitute a regular fuel with an e-fuel that's produced, artificially or not from natural sources, and it just goes into the same equipment. So this has a very big advantage, and it's not to be underestimated, the advantage of being a fuel that can be just thrown in there.
Yeah, let me show a comment. Is electricity a source of energy? No, is not, Domenico.
Yeah, that's a very important concept, because when we talk about energies, a lot of times we're just talking about carriers and so on. And in particular, there's a big confusion with hydrogen, because actually hydrogen can be both. It can be a source in certain circumstances, and it can be a carrier in most circumstances. Electricity is a carrier. But for example, when you have, I didn't even discuss, but some of these nuclear batteries, very low power so far and so on, but they provide electricity at low levels for at constant levels for a long time. They are providing electricity as a source of electricity from nuclear reactions inside. And that is something that's kind of provides a gray area there. Where do we stand? But that's what technology does. It breaks some of our preconceived ideas a little bit.
Yeah, that's right. Cleveland, could you please go to your slides?
Yeah, I just threw a couple things here. This red line in the middle, if people wonder why it's there. What I did is here on the left side, I'm talking about coal to LNG. This is a very large scale process going on. And in fact, as we've discussed in many programs, coal is going to be here for a long time, as fossil fuels will be. But within that reality, there is a very large process going on of converting some coal plants to LNG and natural gas. And this has been in particular, of course, in developed countries, United States, Western Europe, but also in Bangladesh, in Myanmar, and many Latin American countries and so on. This is a reality that people don't often realize, because the developed world is already talking about trying to reduce coal. But even though the developing world is not doing that so much, it is making some conversions. And that is a process, because coal plants are very large, that is a process that every conversion makes a big difference, because all of a sudden you're converting a lot of coal consumption into a lot of natural gas or LNG consumption, which is much lower emissions level. It's still fossil fuels, but that is a big change. And if we were to extrapolate that, which obviously is not going to happen anytime soon, just converting all coal and plants into other types of energy generation would provide tremendous benefits for the environment, not just in emissions reduction, but in actual pollution reduction. Sulfur, nitrogen oxides, and so on, which, of course, translate into people dying. Right below, I talk about hydrogen underground storage, just like methane storage in underground reservoirs, in salt caverns or in reservoirs, if they have adequate, completely sealable cap rocks. But that, of course, presupposes hydrogen being a big part of the energy transition, which I think we discussed before is not so likely, at least not in the near future. But the possibility of providing storage in a large scale, so that now you have storage not for a day or a week, but for months, for example, for winter. This can make some uses of energy viable, whereas before they might not be, because you can't do this in tanks and trucks and so on very well. But underground storage is a possibility, especially if you're right close to where it might be generated. Now, of course, I still have my qualms about generating hydrogen from wind and solar, but if that is the way that a lot of production is going, this is a facilitator. But on the right hand of the red bar, I discussed some things which maybe not in the near term, but maybe in the medium term, can be very important developments. At the bottom, we're talking about thermal sand storage. We already see some installations in Europe. Obviously, this is for the developed world that can afford systems that provide, for example, heat for winter. The developing world does not have much of a problem with cold. They're not in very cold climates in general. But this is a a new technology which is taking off, and it's actually scalable because the tanks are now providing something like 10 gigawatt hours of storage, which is completely not viable with batteries. But you're at a scale now that you can talk about much more than just hours, days, even weeks. You can provide storage for months. And if the scale goes into the terawatt hours, now you're at the point where you can provide seasonal storage with a new technology that's engineering technology, not so expensive. You're basically talking a tank with salt and some tubing and so on. So some of these developments can actually be quite exciting in terms of making a difference not too far in the future.
Nice.
And the last thing is this, the flow batteries, which are making a break from conventional batteries that are enclosed batteries, because now you say we can scale up a battery to almost whatever size we want, because these two, the anode and the cathode, are actually tanks. And you can make tanks very big. You can have liquid tanks that are, thousands, hundreds of thousands of gallons if it comes to that. So now the battery size limitation is supposedly not an intrinsic limitation, because the actual generation occurs at the membrane ion exchange barrier, and the electrodes are on either side of it. But the actual storage of positive and negative charges are actually in a tank, liquid in general, maybe some with solid parts inside, depending on the technology. This is a major technological breakthrough. It probably will take some 5 or 10 years, but the fact that it can be very large scale, that is an impressive achievement for near medium term.
Interesting point. Very attractive point.
Yeah. The other thing I want to say is, Paul touched on this. Scale is very important. I agree. That's why I divided this in scale. And certainly, coal plants and nuclear plants are very large scale energy generating systems, as opposed to even some storage systems. There are pumped storage systems, for example, in hydroelectric plants, that you can pump water up, and they can be very large scale also, depending on how big the lake is, up in the mountains. So scale is very important, but also time frame. And time frame has two components. One is how soon can we expect these things to become viable, and the other is on what time scale do they operate. Batteries we're used to operating on a daily basis. The phone discharges and you charge it overnight. That kind of a fast cycle. But now we're talking about battery systems and storage systems, molten salt, sand, many others that are designed to average out fluctuations on a time scale that can be up to weeks, maybe even months.
Cleveland, how big should be a tank like this you mentioned before to be something viable? For my understanding, should be something huge, like a mountain.
It'll probably be a tank farm.
No, you don't. I mean, it's completely scalable. So you can have one of these flow batteries that are operating, that are working now. Maybe they're not as efficient as other batteries, but that's what technology is working on. And the fact that the tanks are outside, you can have a 1 gallon tank or you can have a 1,000 gallon tank. So the question there is, a 1 gallon tank will provide storage for, say, 1 hour. A 1,000 gallon tank will provide 1,000 hours of storage.
But this is not a technology disruption. It's only a kind of a scale problem. No?
Exactly. Which again, you recognize the batteries were very limited in terms of duration. So now we're breaking the mold a little bit, because the technology in the middle there, we're improving the efficiency, but in terms of storage, we've basically eliminated that problem and put it outside. Sure, maybe they have to be big, but if you have a 10,000 gallon tank on either side of something, if it's an installation that's not size restricted, that can be very important.
Let me show some comments. Oh no, sorry, this one no. This one, Robert Di Domenico, or
Right,
hydrogen.
not a source. Again, yeah, carrier, and in some cases, just a balancing system.
And another comment from him. No are battery sources of energy.
Right. Yeah.
Right.
The only difference there is maybe that nuclear battery, which again is fuzzy area of what is a real battery as opposed to a generating system. Yeah.
Go to the next one.
Yes, sure. Here I talk a little bit about hydrogen because now, say that we're talking 15 years from now, and this is we agree. Hydrogen in a big way in our energy mix is not very close. Definitely, green hydrogen from wind and solar might be something that can pick up in the short term because we have a lot of cheap solar and wind producing electricity. We produce hydrogen. I don't think that is the way to go. And in fact, I said so last time, many years from now, we'll look back and say, look, green hydrogen had this peak, but of course that is not a very sustainable way of producing electricity, even though it's supposedly green because of so many losses and so on. But if we look at hydrogen as a source of energy being produced, say in the mantle or in the center of the earth, and then being migrating upwards into reservoirs or even leaking out, as much of it actually does and gets lost. If we look at that as a way of harnessing that hydrogen and producing it, which we call white hydrogen from naturally occurring accumulations, the whole world has them. And in fact, for example, in this picture, all of the points there show some known accumulations. Those points are not representative at all because this occurs all over the world. We know this from geological theory. It cannot be restricted to Europe and the US because that's where they conducted most of the research. It is everywhere in South America and Africa, Australia, the world. If we begin to harness that in a concerted way, we could be producing hydrogen at significant scale with the same problems we discussed before in transporting it, using it, and so on. It's still a problem. But in terms of availability, that is something that can be very disruptive. We're looking at a lot.
Paul, do you have comments on hydrogen? I know that you like a lot of.
I think Cleveland has covered all the points that I was thinking about. Hydrogen is, we breathe hydrogen, we drink hydrogen. Hydrogen is readily available. It's converting it into an energy source that's where the problems lie. And the storage of hydrogen is also where problems lie.
Yeah. Well, a lot of it has to do with the fact that people didn't understand why there would be a lot of hydrogen in accumulations in reservoirs and so on. But nowadays we understand that hydrogen is constantly being generated by degassing from magmas and so on. There's cataclysms of siliciclastic rocks, minerals. When they come in contact with water, at the interface, there's an exchange and hydrogen is liberated. There is water oxidation of iron minerals that releases hydrogen. And these processes occur underground, at such a scale, which is unimaginable, because we're used to thinking of, hydrocarbons which were produced at some time by living organisms and so on. And now we're talking about something that is being produced at an abiotic scale, as well as biologically, but at an abiotic scale at tremendous levels, so that the production that is going on is very big. Some of it is accumulated and some of it is vented and lost. But now we have a different understanding that hydrogen production by natural geological processes is tremendous. Radiolysis of water by radioactive minerals nearby, that is producing hydrogen. And of course, the hydrogen gets produced, it starts migrating upwards, it
Cleveland,
finds ways to go.
Cleveland, is it true that you need more energy to create energy from hydrogen than the energy that hydrogen delivers back to you? Is it true?
I think when you're talking about, for example, green hydrogen and all these hydrogen sources that we're now talking about, even gray hydrogen from methane reforming and so on, of course, it's not energy efficient, but it provides hydrogen. And of course, refineries need hydrogen, so it doesn't matter. You use up a lot of energy to produce less energy, but in hydrogen. But it's not efficient.
Yeah, but the energy balance is negative in this case.
For the hydrogen that we're used to talking about producing, green, gray, all those, but this white hydrogen, no. The nature is producing it.
But what's the volume of this white one related to the other?
It's many times more than hydrocarbons in the. That gives you an idea, and you know how unimaginably large the hydrocarbon balance in the crust is. It's because it's not even biologically dependent. It's a process that the Earth is undergoing at a scale of many hundreds of kilometers of depth. So, when we talk hydrocarbons, we're talking 10, 20, 30 kilometers. Now we're talking 300 kilometers where this can be going on. And all over the world, we're not just talking in areas that have particular geological structures. We're talking about the Earth's mantle, and the crust is all doing this. So the quantities are unimaginable. We're just not paying attention to where we can go and get this hydrogen. But of course, we're still going to have a problem with what we do with it once we get it. But I mean, in terms of availability, it's just unimaginably a lot. And of course, just to talk on this side, I continue to insist that even though that's true, it's possible that maybe because of the infrastructure that we have from the oil and gas industry all over the world in depleted oil and gas reservoirs, that if we are able to convert some of those depleted oil and gas reservoirs into new production of hydrogen from underground, maybe that can become viable just because all the infrastructure is there, and all of a sudden from the same well that you used to be producing oil and gas, now you can get hydrogen. If it happens to be in a place where it can be easily used, maybe just in generating electricity, for example, and just go and burn it, that's a possibility where hydrogen can become viable also. These are things that might take a little while. That's why I say medium, maybe longer term, but it's there in the works.
But how stable is hydrogen?
Not very, yeah. That's one of its main characteristics. Very reactive.
It easily reacts with oxygen, with carbon. So taking existing fields and trying to extract the hydrogen might react with whatever it's in.
Well, I think the reactive aspect of hydrogen is there, but in terms of producing from underground accumulations, it's probably not a major limitation, because there are accumulations of pure hydrogen and it hasn't reacted with the walls around it or anything. So if it's accumulated in significant amounts And if you extract it the same way, there's no reason why it would react anymore until you want it to react with oxygen, burn it, and drive turbines or drive refineries or whatever you want, even as a fuel. So I think that reactiveness is a problem with transportation, storage, above ground, and so on, because we all talk about how hydrogen as a fuel is a very complicated concept to implement. And much before that, I'm betting, of course, on biofuels, e-fuels, or anything else.
Yeah.
Look at the Domenico's comment.
Yeah, helium is produced currently from methane, from natural gas production separated out. But hydrogen has not been produced from oil wells, because in order to produce it from hydrocarbon accumulations, you need a process, such as I pointed out. I don't want to go into details, but it's a biological process. You actually have to inject microorganisms that convert hydrocarbons into CO2 and hydrogen and other compounds, and then you separate the CO2. But it's a completely biological process where you convert, say, 100 units of energy into 10 units of hydrogen. But you don't care. The hydrocarbon down there is not going to be produced anyway. So the key there is, are you able to get some hydrogen on the surface from old depleted oil and gas wells? So, sometimes you don't care about efficiency. Sometimes you do.
But what about the refining of the gas?
Yeah, I mean, the separation of it. Basically, like nowadays, you have oil wells that produce gas, and you actually separate, as Petrobras pioneered this separation right at the sea bottom, and you just re-inject it. Yes, it's complicated. It may be costly, but that's standard operating
disruption,
procedures.
potential disruption.
And it's scalable.
Yeah, scalable. That's the key, scalable, because now we can be talking about big scale. But it's important to understand that the near term changes that we can foresee, and certainly, we are still seeing a tremendous growth in LNG production, specifically more than just natural gas, that can actually bring about a lot of changes, even as far away as in Asia, which is maybe more reluctant to change its energy mix, because of course it has to prioritize cheap fossil fuels, but even there it's making some of those changes.
Okay, I have three conclusions, and I would like to submit to you to see if I'm right or wrong.
Let's see.
The first, batteries is a major challenge, maybe the most important challenge that we have in the potential disruption in the next years. Is it correct?
I think batteries, yes.
Yeah.
We started with was it nickel cadmium?
Yeah.
Long time ago, had no life. Lithium ion have much longer life, but they still have a hysteresis, and they do degrade. We need batteries that can be used on a large scale or on a small residential scale.
Yeah. So is the most important challenge that we have.
Big challenge.
Yeah. The second point, please. Hydrogen is still a dream for Cleveland, but Paul and Cavagna don't.
I dream about it every day. Yes.
Okay, you agree with that. And the third, scale is not a disruption, but so important that may be something like a disruption.
Well, I think scale is a disruption, because if we can't scale the conversion of that fuel to electricity, we're only going to be. I can't really conclude. It's just, for me, scale is important. And
but scale may be only in the efficiency system. You can scale an efficiency system, so it's not a disruption. It's not something better than before.
Well, imagine if you had the batteries that power the cell phones. If you had them in a gigantic scale, they would still be so expensive because they are expensive proportionately.
Yeah.
They would not be useful. But when we say scale, we generally mean that something is scalable to the level where it can provide storage, say, for uses of weeks or months or seasonal. Then we presuppose that it has to be scaled at efficiency at a reasonable cost. And in fact, some of these systems, as they scale up, can achieve economies of scale. That's what the people in innovation are working on.
Yeah, but also, for example, if you're talking about a house or a car, you have a size of battery that can supply the energy required by that house. There is a very large steelworks, a couple of hours from where I live, that's converting its furnaces from coal to electric.
Yeah.
Now, how would you be able, if you didn't have power generation to provide the electricity, and think about the scale of things that would be required for those furnaces,
Yeah.
working 24 hours a day, 365 days a
Sorry,
year.
I'm wrong in the third point. No problem.
But let me say one other thing. No, come on. Scale is intimately associated with innovation because this is, everybody's tinkering with something in the garage, but to make it work out in the real world and a big industry use it or a big, a steel mill, that takes innovation to break the barriers of inefficiency and so on. And this is something we discussed a little bit last time. Paul mentioned now, artificial intelligence can provide the pathway to make a lot of these things viable. Because right now, no matter how hard we think and we tinker with things, we just can't come up fast enough with ways of improving efficiency. Whereas artificial intelligence has already provided completely unimagined materials from combinations of elements, for example, that people didn't conceive of. And artificial intelligence said, you have to do this, and you mix these metals, and all of a sudden you have an alloy or something with
Yes, Cleve.
properties that
For me, there are three different issues here. Technology disruption is something different from scale or grow something very fast. And the last point, this technologies for digital transformation is totally different from energy disruption.
Yeah, but see, artificial intelligence can make these things happen because even certainly in medical fields, we're talking nowadays, the artificial intelligence will speed up by 10 or 20 or more the speed with which new medications, for example, are developed and tested so that instead of, 5 years, we can do something in 2 months. That is the same thing that can make an energy system that is just a concept now. It's totally not viable. But all of a sudden, if artificial intelligence says this is how it can work, and all of a sudden you say, okay, now we can put it out in the field, it works. And this is happening. It's happening in materials to make motors and so on fit into the kinds of things that it has to fit in order to provide solutions that were just not viable before. It's not a question of size. It didn't work. And now you can make it work. It's unimaginable because we in the energy industry are used to thinking of very unintelligent hardware, gears, motors, that kind of thing. And all of a sudden, we have artificial intelligence inside a computer telling us what to do and coming up with solutions that, none of us, petroleum engineers, geologists, ever thought of.
But the artificial intelligence isn't creating new science. It's just thinking outside the box and how to apply the science that we know.
Exactly. We can wait 100 years, but if it brings it to us this year, then all the better, right?
Good dream. Okay, guys.
Very good.
Thank you so much. It was a pleasure have you in this podcast today.
Yeah, it was good dreaming a little bit.
Yeah, a little bit more. Okay.
Take care. Bye bye.
Take care. Bye bye.
Bye.
Thank you.